All right, thank you. Thanks to the chair for the introduction. Hello, everyone. My name is Wenchao. I'm assistant professor at the University of Rhode Island. Thanks for being here, and thanks for the organizers for making this possible. It's a very nice place to be here. And first of all, I would like to warn everyone that my topic is not on AI in quantum because originally I wanted to just attending and learning about AI in quantum, but when I given the opportunity to give a talk, I forgot about AI and I just talk about something in quantum, which I'm doing. That's the warning. But at the end, there are a couple of slides that I was trying to back in track on AI. Hopefully, I would learn some more perspectives from you and to apply to quantum projects that I'm presenting. So my work is on quantum sensing. And so for pretty much precise sensing is very important for physics. For exploring fundamental physics, there are different examples here. I'm listing a few of them, like atomic clocks, which gives us better and better measuring of time, and searching for dark matter, which is an unsolved physical problems, and as well as electrical dipole moment, which measuring them would constrain CP violations, which are important for standard model of physics, and as well as LIGO, which measures very accurate displacement in space for proving the general relativity, and so on and so forth. So the topic that I'm going to focus on is trapped ions, which is a platform that I have been studied for several years. For those who from quantum computing background, you may be familiar that trapped ions are used for very good platforms for quantum computers for building up these circuit platforms. But on the other side, there are very good, excellent platforms for quantum sensors. I just list a couple of examples. One is using, for example, ytterbium ions for very, very accurate atomic clocks. And on the other hand, with lots of ions, these can be form some crystal and can be useful for detecting extreme weak forces such as electric force, and maybe useful for detect some candidates of the dark matters. That is something I'm going to focus on. And for now, there is the best known best known trapped ion sensors for force sensing are used these ions in penning trap. And forget about the technical details how we form these trapped ions in penning trap. The interactions that we can generate in this type of systems are those qubits with their collective motions. These can be formed physically using lasers, such that these could induce spatially varying AC stock shifts. So as you can see, A plus A dagger are the effective position of one mode of these ions, and SZ are the collective motion, the collective spins. So basically it's a sum of all these spin Z of the ions. And so the motion and the spin coupled coherently, and we can use that to map any forces that are being applied on the ions. Okay, so if we, so this protocol discussed that if we start with coherent or ground state or coherent state of the motions, we can only detect the sensitivity of displacement on the order of 1, according to this Hasselbalch uncertainty principle. But by having this spin motion entanglement idea, one can map, let me see if I have this. Okay. One can map the motion displacement to the spin rotation, which can get you this enhancement factor of f tau. And ultimately, in this work, that one can have this sensitivity of displacement goes inversely with this interaction strength F times tau and gives you this sensitivity limit. And in this protocol, Gilmore et al. From John Bollinger's group from NIST, they demonstrated that the sensitivity of this platform with electric field sensitivity can bring down to about 240 nanovolts per meter per square hertz. And this is comparable with the best known Rydberg electric field sensing. And if they are able to bring the technical noise down, they can bring this to on the order of 10 nanovolt sensitivity, which are ideal for detecting certain types of dark matters. And the question that I'm asking and the project that we are proposing is how we can improve this fundamentally. Forget about the technical detail. Well, the idea that we proposed is this protocol. So you can see the difference between the previous protocol is I'm inserting here 2 additional operations. Okay. So without these 2 additional operations, this is the same as the previous protocol by having this spin motion coupling and then the signal driving and then reverse interaction. And why we are doing this? The reason is that previous protocol focused on mapping the displacement signal to this collective spin rotation, but just measuring with the coherent state of the spin. If we are able to prepare some entanglement of the spin state, we are able to extract this spin more accurately. And so ultimately, if we derive the sensitivity of displacement, it will be given by, instead of just this factor as you've seen previously, we have this additional factor which make it more general. And the reason comes from this term, so-called term quantum Fisher information of the spin states. So if you prepare just coherent spin states, that these are not entangled spin, as in the previous paper, and you will just get this n factor which cancels with that n. But if one can prepare some entangled spin state, then which we would improve this sensitivity by a factor of n. And the actual more detailed steps are given here. Apart from this spin motion entanglement, we have this spin-spin interaction, and in which this can be generated in trapped ions still using this spin motion coupling, but with detuning. Effectively, one would generate something called the one-axis twisting. And this is one type of quantum Ising model which was discussed earlier in one of the talks. And so in addition to generate this one-axis twisting interaction for some amount of strength, we also need to do some rotation about this spin axis such that we would be able to optimize the direction of our sensing protocol. And we also apply this reverse sensing interactions in order to extract the sensitivity. And for the detection part, we want to choose a particular angle of measurement in order to get the optimal detection of sensing. And one critical question in quantum sensing is part about getting the quantum enhanced Fisher information. The critical question is how we can retrieving the quantum Fisher information for optimal sensitivity, which in general is challenging. And the idea that we used in our protocol is the interaction-based readout. So, so this has been studied by many authors, but one of the papers that came into our mind is Schulter et al., and where they consider this one-axis twisting and untwisting protocol, where they have this map of optimal parameters of this squeezing and unsqueezing parameter where you can maximally extract the sensitivity. And at the end of the day, what you are doing is you are measuring just along the spin, not the spin statistics, but just the spin variance along one particular direction, which is relatively easy to perform in experiment. And so ultimately, what we are doing is we are optimizing over the squeezing and unsqueezing as well as the direction of sensing and the measurement projection direction. Okay. This is the fundamental limit, but extracting this limit may not be the best way, but we can do this where this amplitude sensitivity spin projection measurement. So once we do that, this quantum Fisher information will be replaced by this eigenvalues, maximal eigenvalues of the single value decomposition that we obtained through this projection protocol and by optimizing these parameters. So the results that we have is we need to optimize two things. One is the states of the system. The other one is the measurement apparatus, how we optimally measure the system. And here I'm showing some result of these eigenvalues. The larger the better, which shows the enhancement that we can get, and comparing with without decoherence in the system or with some value of decoherence. And you can see how the dark area shows different results. And in the lower panel, we have the optimal directions of the signal in which actually it's the measurement projection in which as a function of this squeezing and unsqueezing parameter. The horizontal direction shows it's along the spin y direction, and the vertical is along the spin z direction. So after optimizing all these technical details, we have made this plot, and this one is in comparison with the previous work, where we show that this green one was the result from the previous work, and we show that we can bring down this amplitude sensitivity by a factor of 15 dB, and so this gives us much more enhancement considering the practical realistic situations that we have over here. And this eventually, if we translate this into some electric field sensing for potentially detecting dark matter, then we can bring down this number from the previous paper to by a factor of 10 from this at around this optimal point, considering both the decoherence and frequency fluctuation, the technical noise, the leading technical noise in the system. So that's pretty much the result that we have obtained so far. And then the question is, I derailed and how I get back to AI in quantum. Well, so the last two slides might be able to answer your question, or might, you can comment on what can be done. There have been two protocols that we found are relevant for our sensing protocols. Basically, the machine learning for quantum sensing. One idea is you can see proposed by Sanders, Hatchell, and Zinn, and some other authors. And the idea is in this Mach-Zehnder interferometer, one wants to extract the unknown phase. One can make the measurement and feedback to this apparatus to tune this phase control. And so this is basically updating the measurement apparatus. And on the other hand, there is an algorithm called the variational quantum algorithm for quantum state preparation for extracting the maximum quantum Fisher information. And by authors including Akira in the audience, the idea is if I don't know the system, and by making measurement and feedback to the system, I can continuously update and my preparation status to prepare the optimal state for getting the maximal quantum fusion information. And so both these ideas could be applied to the trapped ion amplitude sensing. So the idea is we need these parameters, the squeezing and unsqueezing, the signal direction and measurement direction. We need to optimize these points. And so we may not know all the system well. So the parameters or the description of the system is presumably that it could be in that situation. But if it were not in that situation, if we do not know completely about the system, we might not be able to optimize it directly. So, but we can, based on measurement and then feedback to the preparation and the measurement steps, to updating and eventually to working in the optimal point. So that's the AI part for this quantum sensing. And hopefully it will be efficient and robust. But on the other hand, what we are happy is we would directly optimize the sensitivity, but not the quantum fusion information. The sensitivity can approach the quantum fusion information in certain region, but not always. With that, I come to the summary slide that we proposed a double quantum enhanced amplitude sensing by providing the entanglement of the spin states, which gives us the additional enhancement. And we also consider experimentally accessible ways to extract this sensitivity. And the machine learning protocols may be assisted to optimally finding the working points to extract this sensitivity. And of course, the platforms in trapped ions can be extended to other platforms like trapped ions, cavity QED, or circuit QED. And that's all for that. And last but not least, I would like to appreciate my collaborators, John Bollinger, Addison Carter, and others from NIST Boulder. And with that, I would like to thank you very much for your attention. Questions? Yeah.
I guess it's kind of twofold. So you talked about optimizing measurement direction as a way of improving the sensitivity.
Mm-hmm.
One is that would then imply a known or at least constant source direction, correct?
Mm-hmm.
And then the other thing is then, if you wanted to leverage that, could you then measure in two known directions or multiple known directions and use that to determine the source direction to then optimize using that, or is it more abstract?
Okay. So your question is optimizing two known directions?
Well, it's if you wanted to, when you're talking about optimizing the direction measurement, that would imply a constant source of whatever you're measuring, right? A constant direction of that source. If it's varying, then the optimization is meaningless. So could you, if you wanted to determine that direction, could you use chosen directions, say if you measured in 3 directions and used the components? Is it non-abstract enough that you could resolve the source direction of the field you're measuring?
I'm not sure I understand the question. What I can say about the optimal direction is it's there. So for particular quantum states, there are particular sensing direction that is most sensitive to, and if we don't know about where does the signal come from, we have no idea what is the best direction to optimize. But suppose the signal direction is applied, say, along the x direction, then let's just optimize along the x direction and to see if we can get the best signal. But we can also always change the direction and to optimize to the unknown signal and to make it the optimal. Yeah. I don't know if that answers your question, but I'm happy to check about it afterwards. Yeah.
Okay. In the interest of time and not postponing dinner, let's thank the speaker once more.
All right. Thank you.